All right, so let's get started on today's class. So I had originally hoped to take up exam number 1 today, but that needs to be postponed just because of some anomalies with the makeup exams. So we will try our very best to have that for next class. It actually kind of works better next class because we do have a lot of things to cover today. But I did post your grades, and I will be uploading your corrected Excel sheets to Canvas prior to taking them up in class so that you can follow along and see exactly where you got your points. All right, so we're going to continue on today with Chapter 4, these key ingredients for inferential statistics, probability. And once again, let's keep in mind why it is that we need to have these tools, what it is about inferential statistics that is absolutely essential for psychology. So once again, just to remind us, I want us to continue thinking about that group of children. So again, if you graduate and become an educational psychologist, you might be working with children with special needs. So if you have autistic children and you have 14 of them in your class, you might, because of your psychology skills and theories, come up with a new way of teaching these children to increase their learning outcomes. So maybe you discover or develop a new intervention, a new treatment, where you teach them using interactive tablet technology, and then you test to see if that increases their learning outcomes above traditional methods. And let's say that by the end of the semester, you find that your new technique actually does increase their learning outcomes above traditional methods. That is wonderful news. However, without inferential statistics, and this is something to keep in mind, without inferential statistics, that is where the story ends. You have discovered a technique, a treatment that you have determined works for these 14 students. But without inferential statistics, you cannot generalize that to the population of autistic children. So it's very important to remember that without inferential statistics, psychology would be for the few and far in between, and we wouldn't have the power to reach out and make predictions, make generalizations about other autistic children in any other part of the world who are not part of the study. So again, just imagine that scenario where if somebody says, "Oh, I heard you have this treatment for autistic children," and you say, "Yes." And they're like, "Does it work?" And you're like, "Well, it works for my 14 students." And if they asked you, "Do you think it'll work for somebody else?" all you could say was, "I don't know. Maybe it will, maybe it won't." So all those times when you read an article or you discover a new psychological principle and you say to yourself, "You know what? I'm going to use this in this new situation to help hundreds of thousands of people, to help the population of individuals." Again, all of that is possible because of this technique of inferential statistics. So we're going to start building towards that ability to generalize from a sample to a population. And again, it's very important to remember that human minds are horrible at generalizing from a sample to a population. We are very bad at realizing when something is going to be true. If something is true of a sample, will it also be true of the population? Or if something is true of a sample, does that mean that it will not be true of a population? And if you want to take a look at humanity's human beings' inability to determine when something is true of a sample and it is not true of the general population, a very timely example of that is racism. So there are many times when people see individuals of a minority acting in a certain way, and they generalize that to the entire population, right? So if you see one African-American male with a gun on the news, our minds tend to generalize that that is going to be true of the population of African-American males. And as we know, that is just not the case. But it's how our minds are wired. So if we want to do psychology and we want to do it well, if we want to find a treatment that works for a population and be able to generalize to that population intelligently, we need a procedure to take it out of our subjective, biased minds and into some sort of objective procedure, and that's what inferential statistics actually is. So today we're going to continue to develop our abilities in this. Last time we took a look at probability. Today we're going to extend it, start taking a look at the normal curve, take a look at probability and the normal curve, and then take a look at how we're going to use z-scores and the normal curve table to answer the types of questions that we're ready for in terms of percentages and proportions and probabilities of sections of that curve. All right, so the normal curve. We mentioned this curve last time we introduced the idea. The normal curve, the bell curve, this is a distribution. It's a mathematical, theoretical distribution. But the reason it's so widely used is because it often occurs in nature. So the normal curve is that bell curve where you have high frequencies of individuals or scores in the middle regions. And then as the scores get more extreme, you have less and less people scoring in those at those high scores. And as the scores get less extreme on the lower side, you have lower and lower frequencies of individuals scoring for those ones. This is something that happens over and over and over again in nature. So the reason that this occurs in nature a lot is because it occurs when a lot of random factors combine to form a single score. So when a lot of individual factors contribute to a single score, that's when you end up with a normal curve, a normal frequency distribution in your population. So to give you an example of this, a nice visual example of this, we have this little demonstration here for the normal curve. So this is a kind of an hourglass device where you have a bunch of little ball bearings and you flip the device and the ball bearings fall and then they fall into a normal distribution. And the reason they fall into a normal distribution is if you look at the, flip it over, if you look at that bottom part right there, if you can see the little nodes, the little dark dots, those are all little pieces of plastic. And when a ball bearing hits that piece of plastic, it's got a 50-50 chance to go one way, and it's got a 50-50 chance to go the other way. And then there's another row of plastic. And when the ball bearings hit that row, they got a 50-50 chance to go one way and a 50-50 chance to go the other way. And that is repeated through what looks like about 10 to 12 rows of plastic. So what happens? Well, you get very few balls that go left, 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 the whole way down. And that's why there's very few ball bearings that end up all the way left, because that's the only way you get here. You hit the first peg, you go left. You hit the second peg, you go left. You hit the third peg, you go left. You hit the fourth peg, you go left. You go left on all the pegs. There's very few balls that end up over here, because to get this extreme score, you got to go right, 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 in order to get over there. Most of them will end up somewhere in the middle here, because in the middle is where you go right, left, right, right, left, right, left, 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 right, right, left, right. So a number of different outcomes, right? A number of different pegs that you hit that send you either left or right combine to form a single score, a position on this, and you can see that it forms that normal curve. It's just something that occurs in nature. So this again occurs when many random factors combine to form a single score. So I'll give you some real examples of things that occur in the world that fall on a normal curve. So this is the frequency distribution of SAT scores in 2010. And as you can see, the SAT scores fall on a normal curve. What this indicates is that there are many factors that are determining a person's score on the SATs. So some of those factors would include how much time they spent studying for the SAT. Did they get a tutor for the SAT? Do they have high or low IQ scores? Did they spend a lot of time working hard in high school? Did they get enough sleep the night before the SATs? Did they, what else might happen? Well, anyways, a number of different factors. Were they nervous while taking the SATs, right? So a number of different factors all come together to produce SAT scores. And the ones that score up here in the extreme, those are the individuals where all of those factors go in the correct direction. So they have high IQs. They spent a lot of time studying. They got a good night's rest the day before. The people on this side, they're the ones that had every factor go the wrong way, right? So they didn't study. They don't have high IQs. They weren't well rested. They were nervous. They didn't spell their name right, right? It was all these different factors that occurred, but most people will have some of those factors and miss other factors. So again, most people will end up in the middle. And this normal distribution, this is one of the take-home points from today. When you see a normal distribution like this, it means that there's a number of factors that are being combined in order to form this single score. And this becomes very important when you're arguing from normal curves about certain differences that we might see in our world. So for example, there is a difference in the heights between men and women. And this is mostly due to genetic factors. Men are genetically programmed to be larger. But again, you can see that the height for men falls on this normal curve, indicating that there are a number of factors that are contributing to height in males, and the height of women fall on this normal curve, indicating that there are a number of factors that contribute to the height of women. Incidentally, the height of men seems to be about, the average height seems to be about 5'7", 5'8". Average height for women seems to be about 5'3", 5'4". So again, this is in America, adults between 18 to 86 years old. Importantly, and again, this is something we need to remember going forward, not so much in this course, but just in daily life, anytime you see a normal curve, it means that there are multiple factors that are combining to form those particular scores. And this is something that really needs to be understood when you see graphs like this that indicate, for example, the IQ scores of people in, what was this, American youths, 14 to 22. And this was in 1979 when the famous book on this, The Bell Curve, began. So here we have the normal distribution of IQs for white individuals, and here we have the normal distribution for IQs for black individuals. And this was used to argue the point that black individuals are just genetically less intelligent than white individuals. This was put forth to make the argument that white individuals just have higher intelligence than black individuals do. But remember that this curve and this curve here are a combination of multiple factors. So any one of those factors can cause this difference here. So it could be due to racial genetic differences. That is consistent with this data. But it could be due to anything else that combines to form IQ, such as educational opportunities. So it could be that in the areas where African Americans predominantly live, their educational system is just not as good. And you heard about schools that have predominantly black student population using textbooks that haven't been updated, since the early 80s, and just don't have those advantages. It could be due to socioeconomic factors. So it is well documented that the more money you make, the better your children will do in school, i.e., the higher their IQ will be. So this could have nothing to do in terms of differences other than the fact that white individuals tend to have higher socioeconomic status in this society than black individuals. So again, it's important to remember that it is not one factor that causes these differences, and that will prevent you from jumping to that, what our minds would take a look at as almost an immediate conclusion that this has to be a genetic difference. Incidentally, one of the least hopeful studies that I've ever come across looked at the effect of money on educational outcomes. So it looked at the effect of how much money the parents were making in terms of how well their children did in college. And what they found was that the smartest individuals from the low socioeconomic families, so the smartest individuals from poor families, the smartest, the geniuses from poor families did just as good as the lowest intelligence individuals from rich families. So high intelligence plus money is amazing, but low intelligence plus money is as good as high intelligence plus no money in our society. So if you ever want to wonder why we should have free universities, that's a pretty good example for that. All right, anyways, I digress. Back to the normal curve. So this is the normal curve. And as I mentioned, it happens over and over and over and over and over again in nature. And because of that, people have studied the normal curve to understand this distribution, to understand the proportions in this distribution. And what this allows us to do is it allows us to answer questions like this. So if this is the distribution of the population on a particular score, we can ask questions like what percent of the population scored below a score of 1.25. So this is 0 right here. This is 1. 1.25 is right around there. So we can ask what proportion of the population scored below 1.25. What is the area of that blue section of that frequency distribution? So we're going to see today how to answer questions like that. Because again, areas and proportions are equal to probabilities, and we need to be able to find out what is the blue proportion here. And if we were going to do this with a mathematical formula for the area, very difficult. So we're going to see how else we can do this. What scores bound the middle 50% of a population? A lot of times psychologists will ask this question because a lot of the interventions or a lot of the programs that we have for individuals will only work, for example, within a certain region. So you might have a treatment that is going to work for individuals who are not severely depressed, and it won't work for individuals who are severely manic. It's only going to work for individuals in the middle of those. So what proportion of the population or what scores will bound that middle 50% of the population? What scores on this distribution will give you that blue area there? Well, the answer is minus 0.7 and positive 0.7. So once again, that is 0, minus 0.7, positive 0.7. And we'll see how to figure that out today as well. And then the last one, and this is one that will probably be of interest to a lot of you, especially if you're applying to grad school. What score do you need to be to get into the top 10%? So if you're taking your GREs, or if you're looking at your GPAs, and you are looking at a grad school, and the grad school says we typically accept students in the top 10% in terms of their GRE scores, you might ask yourself, well, what score do I actually need to be in that top 10%? And what you're asking is, if I take a look at 10% of this distribution, what score do I need in order to get to that top 10%? And as we're going to see, we're going to be able to find out that that score is 1.25. So if we were going to do this mathematically, just kind of let you know, I don't even understand the formula for the normal curve. Look it up on Wikipedia one of these days. It's massive. So if we were going to do this mathematically, we would have to wait until you were in grad school and had about 3 or 4 more years of math and stats under your belt before we could figure this out mathematically. Thankfully, people more skilled at that than us have already done this. So what we're going to do today is we're going to see how to use that information, use the work that mathematicians and other statisticians have done, and access that knowledge to answer the questions that we want to know, the work that we want to do. So everything that we're going to be using today, the unit normal distribution tables, this can be found in your e-text. This is the appendix. So if you go to your table of contents, if you go to appendix, appendix A is where you'll find tables of the various distributions that we're going to be using throughout this semester. And the one that we're going to be using today is table A1. So again, this is an indication of how often the normal distribution occurs and how important it is, because out of all the distributions we're going to use, it's the first one that comes up. It's A1, the first most important distribution. So again, that's where you can find it, and that's where we're going to focus on today. How do we use this table to answer questions about the normal curve? So one of the first things to realize about this table, importantly, is that it is a table of z-scores in the normal curve table. So the table here is coded in terms of the z-score. So very important to remember that if you're ever going to use this table, you have to have a z-score before you can access this table. Question?
Where did you get that table?
So if you go to your e-text.
I don't know. What is that? E-text?
The e-text, so if you go through Canvas,
oh,
you can access the textbook, the electronic textbook for the course. And if you go to Contents and go to Appendix A, that'll give you all the tables, and we're going to be focused on Table A1.
I don't even see a tab for e-text.
So are you at your modules?
Modules?
My set of here's an e-text.
Does it mean I might not have it?
No, it's part of the
Okay.
e-text in here, and then once that loads, you'll see a little 3-line thing right there, and that'll get you the contents. You got to fill out your modules. All right. So we're going to be taking a look at this table, how to use this table. Once again, first thing to realize is that it lists z-scores. So we are going to have to, if we're starting with a raw score and we want to use this table, we're going to have to transform it into z-scores. So once again, we see that carry through of everything that we've learned so far. If you want to be able to use this table, we got to be able to calculate z-scores. The other thing to notice is that the other two columns here, they have percentages. What that percentage is, it's the percentage of the distribution in a particular area. And I'll more about that to say in a second, but it's a percentage. So this is a way to find a z-score and get a percentage, or start with a percentage and get a z-score. And those are the two things we're going to be using it for today. So let's take a look at a z-score. We'll start off with a z-score of 0.3. So let's say that you have a score and you transform that score into a z-score, and it's a z-score of 0.3, and you want to know what proportion of your population is above a z-score of 0.3, right? So if you want to know, all right, for 0.3, if that was my score, I got a z-score of 0.3 on a test, what proportion of people scored higher than me? How many people beat me on this particular test? Well, what we would do is we would find that z-score of 0.3 right about there, and we would indicate the proportion that is above it in blue. So the area of the curve that we're interested in is this blue area, because that is everybody that scored 0.3 or better. What we want to do is, once we know the area that we're interested in, we can then take a look at one of these two columns. And one of those two columns has that area listed in it. And it's very important not to rush looking at the two columns, because I've seen students make a mistake right at the end and look at the wrong column and get the wrong answer. So importantly, we have this first column here, which is the percentage from the mean, the center of your distribution, to your z-score. So it's that little blue area there between the center of your distribution, the mean, and the z-score that you have. The other column over here is a percentage in the tail. So from the z-score and up, it's that blue area right there. So what we want to do when you're using your unit normal distribution table, I highly, highly, highly recommend draw out your distribution. It takes 2 seconds. You don't even have to be a good artist. You just draw a bell. You don't even need a pen that works. No, you do. You need a marker that works. And you just draw your bell, and we know that it's a z distribution, so the mean has to be, I heard whispers of 0, you're right. So the mean has to be 0. Where's 0.3? I'm not entirely sure, but I know it's on this side. What part of this is above 0.3? Is that area right there. So once I know that I want the area above 0.3, and again, this took me literally under 10 seconds to draw. Once I know I want the area above 0.3, I know immediately that this is not the column for me. This is the wrong column to look at, because that picture at the top of the column does not match this picture that I'm interested in. So I know it's this column to look at, and I take a look at my z-score, go across, see the percentage in the tail, and that's the answer. That blue area of the unit normal distribution here, that blue area that we're interested in, that is 38.21% of the distribution. So if I scored a 0.3 on a test, that means, if that was my z-score, that means that 38% of people scored better than I did. And that's how we use the unit normal distribution table. So that's one of the main ones, how many people scored above. The other thing you can ask is how many people scored below the mean, between the mean and your score. This is basically how much better are you than average, right? So the area between the mean and in this case a z-score of 0.3. Once again, the most important thing you can do at this time, at this stage, is take a moment, and it says flip chart on the marker there, so I've been lied to. Take a moment and draw your distribution. All right, so let me make sure. Use my own stash. Again, it doesn't take too long. So you're taking a look at this and you say, what's the area between the mean and 0.3? Once again, draw your distribution. You know the mean is 0.3. I don't know where it is, but it's definitely on that side. Between the mean and 0.3 is that area right there. And when I finally have this drawn out and I go to my table, I won't get fooled by this column over here, because that picture does not look like what I decided is the area that I want. This is the picture, the column that has the picture that looks like the area that I want. So I go to a z-score of 0.3. I look up the percent in the table, and what that means is that that blue section right there is 11.79% of the entire distribution. So notice when I drew it here, I didn't draw it to scale. I got nowhere near 11.79%. But these drawings are just to help keep you from getting distracted and to help you choose the right column. And I, again, don't know how many times I've seen students get everything correct. We'll see it's a multi-step process. Get everything correct and then choose the wrong column and get the wrong percentage. All right, the last little thing that we can do, and this one is important to bring up because it's not directly shown in the table here, is to do scores below a certain z-score. So let's say that I scored, once again, a 0.3 on a test, and I wanted to know how many people did I do better than? How many people scored worse than I did? So that would be that blue area right there. How many people scored below 0.3? And again, go to a scrap piece of paper, 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, 6 1,000. I'm done. 6 seconds. And you have your little thing drawn. Well, you know, let's take another second and color it in a little bit better than that. All right. So we know that this is 0. It's the mean. This is 0.3. It's on the positive side. This entire portion is the area that's below 0.3. And this is the only one that we need to do a little bit of critical thinking on our own, a little bit of logical deduction on our own, because this situation is nowhere here, right? It doesn't exist in these two columns. So we just need to think about it and break it down into two separate sections. So this is the way that I like to think about it. This area right here is made up of two separate sections. We have this red area right here from the mean to our z-score. And then we have this entire black area here, which we actually don't have to look up. So the first part is a part from the mean to the z-score. So from the mean to a z-score of 0.3, once again we have our z-score of 0.3, that's 11.79. So that area right there is 11.79% of the distribution. What about this other area right here? Well, this other area is half of the distribution, right? It's the mean and everything below. The mean in your z-scores splits your distribution right in half. So we don't even have to look that section up. We know it's half of the distribution. We know it's 50%. So we take that, and to it, we add the 50%, that is that section right there, and we end up with our final proportion of 61.79%, and that is the percentage of people that scored below a z-score of 0.3. Now there's other ways to do this, and if you prefer to do it in another way, feel free, but I'm just going to go over this one way because once again it works. So again, you identify parts of this from the mean to your z-score, look that section up, and then to it you add the other half of the distribution, your 50%, to end up in this case with that 61.79%. Any questions so far? Yep.
It's only at 50 if you want to see whatever's below, basically.
Exactly. So this is, I mean, there's no kind of like hard and fast rule that I can kind of verbalize, but that's one of the reasons why it's very important to draw this out. Because if you draw out your distribution, I'm going to go over here now. If you draw out your distribution and it says what score, what percentage of people is above 1.25? I did that wrong. What percentage of people is above 1.25? Well, if you say, all right, what part of this distribution is above 1.25? It's very clearly that little area right there. So it kind of lets you offload all that thinking from your brain onto a picture that you can refer to. If, on the other hand, the question was how many people scored below 1.25, well, then you can very easily see that it's this area right here, which you're going to have to look up, plus this area right here, which you can see is half of the distribution. So in that case, you would say, all right, I got half of the distribution plus the area that I look up, and that equals, in this case, it would be 90% of the distribution. So again, it might not seem like a step that you need to do, but I would highly, highly, highly recommend draw your distribution, if for no other reason than to just offload all that information from your working memory so that you can focus on this new thing that we're trying to do and not get tripped up. All right, let's take a look at a few more examples. If you had a z-score of 1, so you have a raw score translated into a z-score. In this case, the z-score is 1, and we want to know what percentage of people are above a z-score of 1. Once again, we draw our distribution, and you'll notice that there's only so many distributions that you can draw. So it does get to the point where you will identify that there's not that many different types of these distributions. It will get to the point, wow, that was a horrible marker. It will get to the point where you're going to be like drawing the same distribution again and again and say, all right, 1.0 instead of 0.3 this time. But it's important. It helps you keep track of what it is that you're trying to do. All right, so once again, we have our z-score. We have our drawing. We want to know the area of that blue section. Match it up to a column it matches to this column here, the picture on top of this column here. Find the percentage associated with that z-score in your table, and that is your percentage. That blue area is 15.87% of the total distribution. Between the mean and a z-score of 1, that blue area right there, draw your distribution, match it up to the column here. In this case, it matches to this column, and we can see that that area is 34.1% of the entire distribution. And then finally, if we want to know how many people score below a z-score of 1, once again, draw the situation out. I like to break it up into 2 sections. One, you read off the table from the percent of the mean to the z-score. And then to that, you add the remainder, which is that 50% section, to get your final answer, which in this case is 84.12. All right, we got one last example here, and I just put this one up here because it can get a little bit tricky. But if you ever have a z-score of 0, a z-score of 0 is on there as well, and a z-score of 0 gives you 50% in your tail, because that is the one that cuts your distribution right in half. So it gives you 50% in the tail. It gives you nothing between the mean and the z-score, because the mean is 0 and your z-score is 0. So the area between 0 and 0 is nothing. But the area below it is 50%. The area above it is also 50%. So don't get confused on a z-score of 0. And again, between a z-score of 0 and the mean is 0% of the distribution, because it has it's at the mean. All right, so that is the kind of general way to read the unit normal distribution table. So now let's take a look at how to actually use it. So there are really only 2 types of problems that you can get or you can answer using this unit normal distribution table. And they fall into the following categories. You either start, get rid of these ones here. So the 2 categories are, we're going to do this one first. You start with a raw score, and people are asking you about a percentage, right? You have this raw score, what percentile are you in? You have this raw score, what percent of people scored better than you did? That's the first category. You start with a raw score, you end up with a percentage. The other category is the complete opposite. You start with a percentage, and you got to figure out a raw score. You got to score in the top 10% in order to get into grad school on your GREs. What raw score do you need on your GREs? You have to be in the top 1% of IQ scores in order to join Mensa. What IQ score do you need in order to join Mensa? I don't know if it is the top 1%. I don't know if that's the case. But anyways, those are the 2 types. Start with a raw score and end with a percentage. Start with a percentage and end with a raw score. So we're going to do first, starting with a raw score. So these are the steps where you start with a raw score and you want to get a percentage. First thing you got to do is you got to convert your raw score to a z-score. You cannot use the table with a raw score. That raw score has to be transformed into a z-score. One of the best things about z-scores is that any raw score can be transformed into a z-score, and that unlocks the table. So remember, it's a table of z-scores. You want to use the table, you got to have a z-score. Step number 1, you convert your raw score to a z-score. Step number 2, and this is my own addition, this is not what you'll find in the book. Draw your normal curve. Do this. It is, without fail, the best thing you can do to make sure that you don't mess up looking at a particular percentage. And even if you feel confident with it, still draw it, because it's a 10-second investment that can save you a completely wrong answer. So you draw your normal curve. Step 3, this was in the textbook, make a rough estimate. It's also a good idea. Step 4, look up the percentage associated with the z-score that you got in step 1 on your normal curve table. And then step 5, you check that answer against your rough estimate. So those are the steps to go from a raw score to a percentage. So let's take a look at that in action here. So for a mean of 500 and a standard deviation of 1, I chose these because this is the distribution for the individual sections of the SATs. So something we all have experience with. So for a mean of 500 and a standard deviation of 1, what percentile rank are you if you scored a 333? So percentile rank is the number of people that scored at your score or below. So if you are in the 99th percentile, that means that you're in the top 1%. 99% of people scored as high or below your particular score. So what percentile are you in if you scored a 333? Well, let's take a look at how to answer that question. First thing, step number 1, convert that raw score into a z-score. So step number 0, if you're doing this in the real world, is first ask yourself, which category am I in? And for that, you just read the question and go, did they give me a percentile or did they give me a raw score? In this case, they gave you a raw score and they want a percentile. Category number 1, those are your 5 steps. Now we're do the first step in the category, convert your raw score to a z-score. So we go back to our formula for a z-score. It equals your raw score minus your mean, all divided by your standard deviation. We have all that information. Our raw score is 333. The mean given to you in the question, 500. The standard deviation, 100. We do the math and we find a z-score of minus 1.67. All right, so that indicates that we scored below the mean, right? It makes sense. The mean is 500. We scored 333. Our z-score is negative. Once again, just those little double checks you can do to make sure that you didn't make a mistake somewhere. So we have our z-score. Step 2, draw your normal curve. Not in the textbook, but I highly, highly recommend it. And it doesn't even have to be accurate. So I made this program in Excel just to make these. These are actually accurate, but it doesn't have to be accurate. It just needs to represent the area that you want. So don't worry if you can't draw it out correctly. Don't worry if your bell doesn't look right. Right? All you want to do is you want to say, all right, here's the curve. Here's my z-score of 0. My z-score that I just calculated, minus 1.67, is right there. And do I want everybody above or do I want everybody below? Percentile rank, everybody below. And you draw it, you set it aside, you keep it for step number 4. All right, so that's our draw your normal curve. The next thing you might want to do, or the next thing you should do, is make a rough estimate. And for this, there's a table in the textbook, that one right there, that they recommend that you use for a rough estimate. So this figure here shows the percentages for a z-score of 1, a z-score of 2, and then ignore the 3. The 3 is useless. I don't know why they have the 3 on this. Ignore it. Make a note. Don't use the 3. It shouldn't even be there. Minus 1, minus 2, all good. Minus 3, don't use it. It shouldn't even be there. And what this figure tells you is the approximate percentages between different scores on a unit normal distribution table. So between the score of 0 and 1, there is 34% of the distribution. Between a score of 1 and 2, there is 14% of the distribution. And above a score of 2, not between 2 and 3, but above a score of 2 is the last 2%. So you can see that we got 34% plus 14%, that gives us 48, plus 2%, that gives us 50%. That's how the upper half of the distribution is split up. 34% between 0 and 1, 14% between 1 and 2, and the remaining 2% above a z-score of 2. The distribution is symmetrical, so on the other side, between a score of 0 and -1, 34% of the distribution. Between a score of -1 and -2, 14%, and -2 and below, we have our final 2%. So how do we use this in order to make an estimate? Well, we find our z-score that we found in step 1 on this distribution here. So our z-score was -1.67. There's -1, there's -2. Our z-score is somewhere in there. And then what does that tell us? Well, it gives us a range that we should find in terms of the percent we're looking for. It gives us the range that our final answer will be within. Because we know that that is 2% of the distribution. And our z-score is higher than that. So our final answer, the percent that is below our z-score, first thing we know is it has to be bigger than 2%, right? Because this section is 2%, our section is more, so it has to be bigger than 2%. That's the first piece of information we get. The second piece of information that we get is that our section is less than this entire section. So this is 14%, this is 2%, so our section is less than 14 plus 2, or 16%. So by reasoning through this and making a rough estimate, we know that when we finally look up our answer on that table, we should get a number between 2 and 16%. If we do not, something went horribly wrong. So this rough estimate is, again, just a check. And between drawing the distribution out and making that rough estimate, you are very unlikely to make an error. So we make our rough estimate. We know it's got to be somewhere between 2 and 16%. And then we are now ready to look up the percentage associated with that z-score in the unit normal distribution. This is where we encounter our first hiccup, because you will notice our z-score is -1.67. But nowhere in this table will you find -1.67. And the reason for that is back in the day when these tables were actually printed out on paper and people wanted to make sure that their textbooks were not this large, they were only about this large, what they did is they decided that because the distribution is symmetrical, they're only going to print the positive side. So we need to do one little final bit of mental gymnastics and realize that we can use 1.67 to stand in for -1.67. And we look at our picture and we say, all right, what part of our picture do we want? We want this section in the tail. So if we want the section in the tail, which one of these is the section in the tail? Well, it's not this one. It's this one that is the percentage in the tail. So we look basically for the mirrored flipped image of what we drew. That's right here. So we look up our z-score of 1.67. We go across here. Whoops. We go across here and we find a percentage of 4.75. So the last thing we do, now that we have our percentage here, 4.75, we check our answer against step 3. We estimated that the percentage should be between 2 and 16%. 4.75 is between 2 and 16%. So we know that we got confidence that we read the table correctly. And that is our final answer. So if you, on your SATs, scored a 333, that puts you in the 4.75th percentile, meaning that 95% of people scored higher than you, meaning that you probably want to take those SATs again to try to improve your score. All right, any questions on that? Those steps right there. All right, that was category number 1. You start with a raw score, you end up with a percentage. The only other thing that we're going to be doing is the complete opposite. You start with a percentage, you end up with a raw score. So for this one, starting with a percentage, this time you're still drawing your normal curve. So step 1, draw your normal curve. Step 2, make a rough estimate. Step 3, look up the z-scores associated with that percentage on your normal curve table. Step 4, check that answer against step number 2, your rough estimate. And then finally, step 5, you got to convert your z-score to a raw score. So once again, we're going to be using z-scores. So anytime you use that unit normal distribution table, at some point you're going to be encountering z-scores. If you're not, you did something incorrect. So remember, we're going to encounter z-scores regardless of which one of these we're doing. So let's take a look at a question. So once again, let's say that you are trying to get into a very prestigious, very exclusive university, and they required their students to have SAT scores in the top 1%. So the question then is, if your distribution has a mean of 500 and a standard deviation of 100, which the individual SAT scores do, what score do you need to get into that top 1%? What is the raw score that you need to get into the top 1%? So notice we're starting with a percent. We want to get to a raw score. First thing we do, draw your normal curve. This is a normal curve that is drawn to scale, but it is just as effective to draw a normal curve that is rough and is not drawn to scale. So once again, we want to know what score do we need to get into the top 1%. So there it is, drawn to scale. And all you need to do is draw your distribution and say, all right, that is the top 1%. Notice, completely not drawn to scale, doesn't matter. That's the top 1%. We're looking for that z-score right there. So it just, again, lets you know which area of the curve you're going to be looking for. Step number 2, make your rough estimate. So once again, we go back to this table. And once again, we know that we want to be in the top 1%. So this time, the situation is a little bit reversed, because instead of looking for the z-score, we have to look for the percent. So this right here, this area is the top 2%, right? Right there is where the top 2% begins. We have to go even further. We got to get into that top 1%. So that top 1% is going to be this area right here. Again, ignore that +3. I don't know what it's doing there. But that top 1% is going to be this area right here. So when we identify what portion of this rough estimate curve is the area that we're looking for, then we can predict, or we can make a rough estimate of what we need to find. So our rough estimate is that our z-score has to be greater than 2. Because a z-score of 2 is where the top 2% is. We want even a higher value. We need to have an even higher value to get to the top 1%. So we don't know what that value is, but we definitely know it's going to be bigger than 2. So once again, we got this range that we're looking for, this time bigger than 2. That's our safety check, and we do it with this rough estimate. All right, finally, we are ready to look up that z-score that's associated with that percentage on the normal curve table. And again, this time we're going in the opposite direction. So first thing we do is we take a look at our drawing and we say, which column do we want? So we want this top 1%. That's the area that we want. We take a look at this column. That picture doesn't match. It's the wrong column. So we are going to stay in this column over here. This is the column that we want. And what we do is we scroll through that column until we find 1% in the tail. Now, sometimes you're not going to be able to find 1% exactly. This is one of those times. Or you're not going to be able to find your exact percentage. This is one of those times. If that occurs, use the one that is closest to the percentage you're looking for. So we got 1.02% here. We got 0.99% here. 0.99 is closer than 1.02, so we're going to use that for our 1%. So there's our 1% in the tail. And then what we do is, again, We take a look at our estimate. Our z-score that we find has to be greater than 2. So we found our 1% in the tail. We scroll across. We get our z-score right there, 2.33. Makes sense, consistent with our rough estimate. So we then get our z-score of 2.33. We check. It is greater than our estimate. So that gives us confidence that we looked up the right area of the table. And now the final thing we need to do, and we've done this before, is we need to convert our z-score into a raw score. So we have a z-score of 2.33. So we use the formula for going from a z-score to a raw score. We have our mean of 500. We have our standard deviation of 100. We get that from the question. We found our z-score of 2.33. We plug that all in. And if you want to be in the top 1% in SAT scores, you need to score a 733. So what score will get you in the top 1%? That score is 733. That is the score you need in order to get into the top 1%. So again, those are the two things that we can do with z-scores. We can start with a raw score, with a unit normal distribution table. Start with a raw score, end with a percent. Or start with a percent, end with a raw score. The two things that you're always going to do. Number one, draw your normal curve. Do it. Please, I don't know how many times, especially on the exams, when I've collected students, sign-in sheets, and I did not see normal curves drawn, that their answers were incorrect. It might seem like an unnecessary step. You might have the confidence that you know what to do. But again, why keep it all in your mind? Why put that extra stress on your mental capacity when it takes less than 10 seconds to just draw it out? So draw your normal curve. And then in both of these situations, at some point, you're going to encounter a z-score. You're either going to take your raw score and transform it into a z-score so you can access the table, or you're going to access the table and find your z-score and then have to transform it into a raw score. One way or the other, raw scores are going to be there. All right, so that is all that I wanted to cover for today. Any questions before we kind of wrap this up?
What if it's equal distance? Because like, if you're, because you had 99 and 102, but the next one was 102 and 104, what if you had 103? Do you go down?
If it's equidistant, there's usually no convention on whether you go high or you go low. That's actually a bit of an issue because one of the more popular percentages in psychology to look for happens to be equidistant between two of them. So in the real world, as we're going to see when we go to using a statistical package, they can find it exactly. So we're going to kind of bypass the table. But for your homework, try both. If you put in one and it doesn't work, try the other one. For the exam, I've pre-programmed it so both will be correct. Okay. So that's kind of the unsatisfying answer, I guess, for that. All right, any other questions? All right, so let's wrap this up for today. So you are now ready to do your homework assignment number 6, chapter 4, part 1. So that involves questions about probability and other concepts that we have covered. And as always, by now you've done your chapter 4 pretest. If you did not get 100% on that, make sure that you go into the MyStat Lab study plan, completing those mastery points so that you can increase your score on your pretest. So that is all that I wanted to cover for today. So we got 15 minutes left. If that's enough stats for you and you just kind of want to let this sink in, feel free to call it an early day. Otherwise, if you want to start up on some of your homework, for example, try out some of these concepts, feel free to do that as well. Call me over if you need help. And the rest of today's class is devoted to in-class practice. Other than that, we are done for today.